Welcome. In today's video, we're going to take a look at an introduction to the idea of mathematical induction. In particular, we're going to look at induction and its use in proofs of equality. So what is mathematical induction? Well, mathematical induction is a proof technique that is usually used to prove a statement about the positive integers or the natural numbers. Typically, this statement that we wish to prove is known as a proposition. So, for example, we may wish to prove the proposition 1 plus 2 plus 3 plus all the way to some number n, and in fact I should say some positive integer n, is equal to n divided by 2 times n plus 1. And here you notice that this is a statement or a proposition. It is specifically to do with n in the natural numbers, and again I'll say the positive integers and the natural numbers are interchangeable in terms of what they mean. And what we actually have here is this formal notation, or a little bit of formal notation, P of n, which is a proposition about the natural number, the integer n. Proposition about the integer n, and we want to make sure that that proposition that we've just stated here is true for all n in the natural numbers. So to prove something like this, we will have a two-step process. The first step is called the initial step, and the second step is what we call the inductive step. And let's explore what those mean a little bit more. So the initial step in an induction proof proves that the statement holds true for n equals 1. In other words, if we have a look at this proposition here, we want to make sure that this is true specifically when n equals 1. So that is the first step. Now, I've been a bit sneaky here. Sometimes the proposition Pn isn't valid for all natural numbers. Sometimes the proposition is only valid for values of n greater than some fixed value n, and I'll show you what I mean by that in an example. So for example, if you consider this proposition here, the proposition 2 to the power of n is greater than n squared. This proposition is only valid for n greater than or equal to 4. So for example, if you plug in 1 into this proposition, we have that 2 to the power of 1 is greater than 1 squared. That seems true. 2 is greater than 1. But if we plug in, say, for example, 2, well, let's actually plug in 2. So we've got 2 squared is greater than 2 squared. Well, greater than or equal to 2 squared. That seems reasonable as well. That's true. They're equal, but it still means greater than or equal to. But what if we try 3? Well, 2 to the power of 3 is... let's have a look. 2 to the power of 3 is 8, but 3 squared is 9. So that proposition isn't true. So in this case, what we'd say is it's only valid for I. And if we try n is greater than or equal to 4, we've got 2 to the power of 4 is 16, and 4 squared, which would be 16 as well. We know it is true for n equals 4. But in fact, it turns out this proposition is only true for n greater than or equal to 4. And so what we'd say is our initial step in this case would be to try and prove that it's true for n equals 4, not n equals 1. Now, the second step in a mathematical induction proof is this idea of the inductive step. And what the inductive step does, and we'll see a little bit more of the mechanics of how the inductive step works. But the inductive step says, well, let's assume that it is true for some value. we want to show that given that it is true for some value, then it will be true, or for some positive integer, I should say. Given that it's true for some positive integer, we want to show that if it is true for this positive integer, then it is true for the next positive integer. And this is what I say. If it is true for some value k, then it is also true for some value k plus 1. So if that is the inductive step, that is the powerful step. And I'll show you why that is so powerful. Well, the inductive step ensures that, well, if it's true for n equals 1, then the inductive step ensures that it is true for the next value in the series, which should be 2. And now that we know it's true for 2, it's true for n equals 2, then it also has to be true for n equals 3, because for each successive step, we've proved the inductive step proves that it's true for the next step in each case. And again, if it's true for n equals 3, then it must also be true for n equals 4, and so on and so forth. So a commonly used analogy to describe the mathematical induction technique is this idea of the domino effect. And the domino effect is this. The first domino falls. When any domino falls, the next domino in the line falls as well. And therefore, all dominoes will fall. And that's kind of like the analogy that I'm going to use to describe how mathematical induction works. Now let's try and get into the nitty-gritty of exactly how we do this inductive step. So, let's begin with this example that I went through before. Using mathematical induction, prove that 1 plus 2 plus all the way to the n is equal to n over 2 times n plus 1 for all natural numbers n. So, your first step in an induction proof is always to define the proposition Pn. So in this case, I'm going to define, let Pn be the proposition that, and then we can realistically just rewrite our proposition that we had on the previous page. That is the first kind of idea of the proof. So then, if we remember, our next step in an induction proof is always to show that the first case, or the initial step, we've got to prove the initial step. So, for n equals 1, we're going to look at the left-hand side of this proposition, or of this mathematical statement. The left-hand side is 1 plus 2 plus all the way to the n. In this case, we've only got n equals 1, and so in fact, it's just the sum of the first natural number. So the left-hand side is simply equal to 1. The right-hand side is what we do is we'd substitute 1, n equals 1, into the right-hand side. And this gives us 1 over 2 times 1 plus 1. And of course, this is equal to 1. And you'll notice that the left-hand side is equal to the right-hand side. And so we can say, since the left-hand side equals the right-hand side, then Pn is true for n equals 1. Okay, we have finalized the initial step. We have proven the initial step, or we've done the initial step. Now comes for the real challenging part of this, part or problem, which is the inductive step. So let's go through that now. So the inductive step, what we're going to do is we're going to assume that Pn is true for some n equals k. And we call k the dummy variable. It's kind of like a dummy variable. We pretend it's just, well, it is a variable, but it's a dummy variable. And what we want to do from here is show that it's true for k plus 1. So if it is true for this dummy variable k, then we know that 1 plus 2 plus all the way to k is equal to k over 2 times k plus 1. Essentially, this is the proposition rewritten, except instead of using n's, we've used k's. But remember, we haven't shown that it's true for n, all n. We're just assuming it's true for some k. So now, what is our goal here? Well, now we're going to have a look at exactly the proposition when n equals k plus 1. So When n equals k plus 1, what we have is the left-hand side of the proposition. Remember, the left-hand side of the proposition was the sum of the first n numbers. This gives us the sum of the first k plus 1 numbers. So you notice here, because we've got n is equal to k plus 1, this value of n changes to k plus 1. And of course, here we'd have the previous term in the sequence, which is k. So again, this is what the left-hand side of the proposition looks like when we've got n is equal to k plus 1. Now, here is the fundamental procedure, I suppose, of a mathematical induction proof, is to insert the assumption that we've made inside this next section. So you see here how I've got 1 plus 2 plus all the way to k. So instead of rewriting that again, what I'm going to do is I'm going to take our assumption and I'm going to take this particular expression for the sum of the first k integers, and I'm going to insert it into our next line of working. So here, that has been replaced with that assumption. And that is the key step that you will use. Now from here, what I want us to do is to make this look like the right-hand side of the equation. And I'll go through how we're going to do that exactly now. So if you remember, the right-hand side of the equation is n over 2 times n plus 1. So here what I'm going to do first is I'm going to factor out the k plus 1. So here I've got a k plus 1 and I've got a k plus 1 here, which is k plus 1. And then I've still got my k on 2 and of course another 1 of k plus 1. Then I'm going to factor out the 2, the half here. So you notice here I factored out a half from this bracket here, leaving me with k plus 2. And finally, I want us to recognize that, remember, n is equal to k plus 1. So I can replace the k plus 1 with n, or just n, and I can replace the k plus 2 with n plus 1, again because n is equal to k plus 1. And now we've actually proven, for at least n is equal to k plus 1, we've shown that n, or 1 plus 2 plus all the way to n, is also n over 2 n plus 1. So by assuming this property here, what we've actually managed to do is to show that the proposition is also true when n is equal to k plus 1. Therefore, and so what we've shown is if P of n is true for n is equal to k, then P of n is also true for n is equal to k plus 1. That is the fundamental part of the induction proof. Now, since P of n, and here is the final statement that puts the cherry on top of the proof. What we are to say is, since P of n is true for n is equal to 1, and P of n is true for n is equal to k, implies P of n is true for n is equal to k plus 1, then by the principle of mathematical induction, Pn is true for all n in the natural numbers. This is the beauty of mathematical induction. So let's have a look at another example, very similar to the first one, of how we're going to use mathematical induction. So example 2 is going to ask us, prove that 1 squared plus 2 squared plus all the way to n squared, the sum of the first n squares, is equal to this expression here, n over 6 times n plus 1 times n 2n plus 1, for all elements of the natural numbers. Well, again, we're going to start by labeling the proposition as Pn. So let Pn be the proposition that again repeat the mathematical formula that we came across. So again, the base case or the initial step that we're going to look at is n equals 1. So for n equals 1, we have that the left-hand side of the equation, which is this left side of the equation, is just 1 squared, which is equal to 1. And the right-hand side would be this side here, which we're going to, again, substitute in 1 as our equal to n. And it turns out that when we do substitute in 1 into the formula here, we also get 1. So again, this shows that since the left-hand side is the right-hand side, then the proposition is true for n equals 1. So now, again, the assumption step, the inductive part of the proof, we're going to assume it is true for some n equals k. So here we've got 1 squared plus 2 squared plus all the way to k squared follows that formula that we had before. Again, k is a dummy variable. And now we're going to do, or we're going to look at what the, we're going to try and prove that the left-hand side is the right-hand side when k is equal to, also when n is equal to k plus 1. So again, to begin with, the left-hand side is equal to 1 plus 2 squared plus all the way to n squared. Now I'm going to replace the sum of the first n squares as, again, notice here I've replaced n squared with k plus 1 squared, which means the term previous to that would be k squared. So again, we've replaced n with k plus 1. So now I'm going to use this assumption that we have here. Remember, the assumption is that this particular summation here, 1 plus 2 squared plus all the way to k squared, is given by this mathematical expression above. So I use that in my proof. I insert that into my next line of reasoning. And so now what we've got is that is the most fundamental part of the proof. And now it's going to be a matter of making that left-hand side, or this expression here, look like the right-hand side. And to do that, what I notice is that I've got this k plus 1, and I've got this k plus 1 squared here. So I can take k plus 1 out as a common factor. So that if I take k plus 1 out as a common factor, and I've got the 6, or actually I took out k plus 1 over 6 as a common factor, which leaves me here with, I've got the k and the 2k plus 1 left here, which gives me that side. And I've actually got 6 times k plus 1, because you notice when I multiply 6 times k plus 1 times the outside here, I get back to k plus 1 squared. So I've been a bit sneaky there, but I've taken out the 6th as well as a common factor, but therefore I've pre-multiplied by 6 here. So then I'm going to expand the innermost part of the, or I'm going to expand that set of brackets. And when I do expand that set of brackets, I've got my 2k squared here plus k plus 6k, which gives me plus 7k. And then finally, I've got plus 6 here at the end. And one more step after that, I notice that this is factorizable. And in fact, it factors into k plus 2, 2k plus 3. And now we're starting to look something very similar to the original proposition. Remember the original proposition, I'll go over the next slide. What I've done here is I'm going to substitute in, or I'm going to recognize that k plus 2 here can be written as k plus 1 plus 1. The 2k plus 3 can actually be written as 2 times k plus 1 plus 1. And actually what I've preempted here, I've rewritten the k plus 1 as n. Because now you'll notice if the k plus 1 is n, then you'd have n here and you'd have n here. And actually that's what I've done just on this slide here, I've just rewritten here what we have, and then in fact I can replace the k plus 1s, all the k plus 1s, with n, and you'll notice that that is in fact equal to the right hand side of this equation. So again, what we've done here is we've inserted our assumption, and then we've shown that the left hand side is indeed equal to the right hand side of this equation. And because Pn is true for, or we've shown that Pn, if Pn is true for n equals k, then Pn is true for n equals k plus 1. And since Pn is true for n equals 1, and Pn is true for n equals k implies Pn is true for n equals k plus 1, then by the principle of mathematical induction, Pn is true for all n an element of n. And that concludes this video.